I'll be presenting to you my final project for Engineering 1050 class. So my final project is entitled the Inverted Pendulum Project, and here I have written a script, a code, to simulate how an inverted pendulum would locate itself back to equilibrium or close to equilibrium, as we're gonna see in the simulation. It never actually approaches it. So in this file, in this script, we start off by just setting the parameters and the initial conditions for our pendulum to obey, what reference frame we are given, and the quantities, the variables, the angle, and what final position we wish that pendulum finds the equilibrium on. One thing to note is that all these conditions are centered around the nonlinear equations of motion. So this pendulum would have been uh, much more simplistic if I would have used the linear equations of motion. However, using the nonlinear ones leads to having to take into account much more variables and leads to much more interesting coding applications that I found through my project, being able to do research and encountering and being able to overcome certain issues. This aspect of the project I found a lot more interesting. So here, for instance, we start off with the reference conditions. We are asked the final position of the slider. So this is the position at which the pendulum and the pendulum slider will try to approach to find equilibrium point at that. So here we have it set at minus 0.5. When we run the simulation, this means that the slider will try to find equilibrium at minus 0.5. However, we can very easily set it to minus 1, for instance, and now the pendulum will try to find equilibrium at this minus 1 location. As we can see, following through that, we have more initial conditions. One thing to note is on our theta 0 angle, here I've set an upward critical angle of 37.275 degrees. This is if we were to use when applying the nonlinear equations of motion, we found that for the specific set conditions we have of our pendulum bar, for example, here the mass and the lengths we have used, it will be unable to return to equilibrium in the given set of distance that we have allowed the slider to operate in. So this angle could be altered, but we would have to go through all equations again and change these parameters from our nonlinear equations of motion. Here again we have the control sliders and a control pendulum. I found this project very interesting as well, as it required the use of Simulink, so running the simulate control and feedback loops and seeing how those two would operate together, as well designing the slider and the pendulum, even though they are not intricate designs, was quite interesting, be able to integrate this extra aspect into MATLAB, and is something that I definitely really much enjoyed. And the final part of this script is running and getting the results from the Simulink project. So from our Simulink feedback loop, going through that is running the equations, feeding it back into our MATLAB script, and then feeding it into the animation. So here we have the units, the pixels, and the positions, describing everything and describing the motion of those pixels to then concentrate around that reference point where we wanted to find equilibrium. And here we are just showing how we will get to that animation. So this is a global overview of my code. I would suggest when running it with different parameters and initial conditions to see the speed at which the slider and pendulum would approach equilibrium, or the different points at which it could approach and whatnot, and then analyzing as well the Simulink control feedback loop to see how those two interact with the MATLAB. And if we just want a general overview of how the integration of this should be, it's much simpler to just look at the original nonlinear equations of motion. So thank you very much, and I hope you enjoy.